Hi, welcome to the class of Complex Analysis, Probability and Statistical Methods, 18 Mat 41. Today, I'll be teaching a topic in Calculus of Complex Functions, that is Module 1. The topic name is Type 2, Construction of Analytic Function given its real or imaginary part. So we'll be working problems on construction of analytic function given the real or the imaginary part of it. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Now we'll see the working rule in the Cartesian form first. Given u or v, the real or the imaginary part of the analytic function, as functions of x, y, we first find ux, uy or vx, vy and consider f dash of z is equal to ux plus I into vx. Given either the real part u or the imaginary part v as a function of x, y, we first find out the partial derivatives ux or uy. Suppose u is given, we can find out ux or uy. And suppose v is given, we can find out vx, vy. And we consider the expression for f dash of z, which is ux plus I into vx. We use CR equations in f dash of z and substitute the partial derivatives. Now suppose I'll be given with u and I find out ux and uy, then I'll be knowing only ux. So I'll not be knowing vx, so we use CR equations vx is equal to minus uy and change this vx in terms of uy so that we can substitute both the partial derivatives. Similarly, the other way, when v is given, we can find out vx, vy. And since vx will be known for us and ux will not be known, we use CR equations to change ux is equal to vy. And then we will be able to substitute the partial derivatives. So that is how the CR equations comes into place. Put x is equal to z, y is equal to 0, the Milne-Thomson substitution to obtain f dash of z as a function of z. So Milne-Thomson substitution helps us to obtain the function as a function of z. So we can obtain f dash as a function of z. Integrating with respect to z, we can obtain f of z. So this is the working procedure to find the analytic function f of z in the Cartesian form. Similarly, now we can see working rule in the polar representation. Given u or v as functions of r, theta, we find the partial derivatives ur u theta or vr v theta. Suppose u is given, we can find the partial derivatives ur u theta, or if v is given as a function of r, theta, we can find out vr, v theta. And we consider the expression for f dash of z in the polar form e power minus I theta into ur plus I into vr. This is the expression in the polar representation for the function f dash of z, which we have seen in the derivation of CR equations in the polar form. Now we use CR equations in the polar form and we substitute that in the f dash of z, and later we will be substituting the partial derivatives so obtained. So f dash of z, either we will be knowing ur or vr, since either u or v would have been given for us. So the other one we are going to change using the CR equations, similar to a Cartesian representation. Now we make use of the Milne-Thomson substitution in the polar form. R is equal to z and theta is equal to 0. This helps us to obtain f dash of z as a function of z. So substituting MTS, Milne-Thomson substitution in the polar form, R is equal to z and theta is equal to 0, it will help us to reduce f dash of z as a function of z. So that by integrating with respect to z, we obtain f of z as a function of z. So this is the procedure in the polar form to obtain the analytic function f of z given its real or imaginary part. Now we can see problems on the same. Now we will see problems. Problems on construction of analytic function f of z given either the real part or the imaginary part. So either the real part u will be given, or the imaginary part v will be given for us. So let us see problems. So first question, find f of z given u is equal to e power minus x into x cos y plus y sin y. X cos y plus y into sin y. So given u is equal to e power minus x into x cos y plus y sin y, we have to find out f of z. Hence find, continuation of the question, hence find the imaginary function, v. Hence find v. So let us consider the given function u first and find out the partial derivatives with respect to x and with respect to y, that is ux and uy. And with that, we can consider the expression for f dash of z. To obtain f dash of z as a function of z, we can substitute Millet-Thomson substitution. Then later, by integrating with respect to z, we can obtain f of z as a function of z. So that is the procedure. We have already seen the working procedure. So let us do the solution. Now given u is equal to e power minus x into x cos y plus y sin y. Let us find out the partial differentiation with respect to x. So ux and uy. With respect to x, when we want to differentiate, we need to apply the product rule. So first I will keep e power minus x as it is. Differentiation of the bracket term I am doing. With respect to x partially, cos y is a constant into differentiation of x is 1 plus y sin y is a constant. So differentiation goes to 0 plus we are continuing the product rule. So x into cos y plus y sin y as it is. Now differentiation of e power minus x is minus e power minus x. We applied the product rule. I'll just explain once again the product rule for you. So e power minus x outside term as it is first. Within the bracket, whatever the term is there, we are differentiating it partially with respect to x. So with respect to x, cos y is a constant in the product. Keeping cos y as it is, differentiation of x is 1 plus y sin y entire term is a constant with respect to x partially. So differentiation goes to 0 plus the bracket term, continuation of the product rule, the bracket term that is v term I am keeping as it is, x cos y plus y sin y, and differentiation of e power minus x is minus e power minus x. Now we will retain this as it is by writing down e power minus x common. We will rewrite this expression now. So this becomes ux is equal to e power minus x overall I will take common. What do we remain is cos y minus x into cos y minus y sin y. We have e power minus x. Here also there is e power minus x in the last term. But we observe there is a minus sign to be multiplied for both of these terms. So when we multiply minus, it becomes minus cos y and minus y sin y. And here we just have cos y. I have written it positive cos y as it is. So this is the expression for ux. Now similarly, let us find out uy. So let's find out uy means partial differentiation with respect to y, considering u term. So e power minus x is the outside term, which is a constant, writing down as it is. Now x is a constant as it is within the bracket. Differentiation of cos y is minus sin y. Now we have to apply product rule for y sin y, which will be y into cos y plus sin y into 1. So we are applying product rule. E power minus x we have kept as it is because with respect to y when we want to differentiate, this is a constant. So keeping e power minus x term as it is, we are differentiating only the bracket term. So in that again, x is a constant, writing x as it is. Differentiation of cos y is minus sin y plus y sin y, we have to differentiate applying the product rule. So y into cos y, differentiation of sin y is cos y plus sin y into 1. So this is the expression for uy. Now the purpose of finding the partial derivatives ux and uy is, now we will consider the expression for f dash of z, f dash of z, and using CR equations we will change both the terms with respect to ux and uy only, ux and uy only, so that we can substitute the expression for both ux and uy, right? So let us do that. Consider f dash of z. The expression for f dash of z is ux plus I into vx, ux plus I into vx. Now we need to use CR equations and change Vx, because we don't know the value of Vx to substitute. We know Ux to substitute, but we don't know Vx. So let us use CR equations. Since given function will be analytic, we can use CR equations and change Vx as minus Uy. Vx is equal to minus Uy using the CR equations. Same thing we are going to apply now. So using CR equations, Vx is equal to minus Uy. So since Vx is equal to minus Uy, now we can change f dash of z as Ux minus I into Uy. Now we know both of them to substitute. Ux also is aware and Uy is also aware of the value. So now we can substitute both the expressions and we can use Milne-Thomson substitution. So in order to substitute both the values, we are rewriting this f dash of z. So ux is e power minus x into cos y minus x cos y minus y sin y. So f dash of z will be e power minus x into cos y minus x cos y minus x cos y minus sin y. Let's check whether it's correct. So this is e power minus x into cos y minus x cos y minus x into cos y minus y sin y minus y sin y. This is ux. We have minus I into uy. Uy is nothing but e power minus x into uy is nothing but e power minus x into minus x sin y minus x sin y plus y cos y plus y cos y plus sin y. So these are the expressions of ux and ux and uy for us, what we had already obtained the partial derivatives. Okay. Now, after substituting for ux and uy, we are now trying to substitute Milne-Thomson substitution, what we are already aware of. So let us use Milne-Thomson substitution. Using Milne-Thomson substitution, we put x is equal to z and y is equal to 0. Once we substitute x is equal to z and y is equal to 0, this will reduce to as a function of z. So wherever x is there, let us substitute throughout as z, and wherever y is there, let us substitute throughout as 0. So we have f dash of z is equal to f dash of z e power minus z into cos 0. Because we are substituting y is equal to 0, cos 0 is 1 minus z into cos 0 is 1 minus sin 0 is 0 or y is 0. Similarly, minus I into e power minus z e power minus z is multiplied with entirely 0. Why is it 0? Let me tell you. It is sine 0 in the first term, which is 0. Y is 0, so second term is 0. Sine 0 is 0, so third term is also 0. So entire imaginary part vanishes. We have expression for f dash of z as, let us rewrite f dash of z, which we are obtaining in simple, which is e power minus z into 1 minus z. So which is same as writing e power minus z into e power minus z. If at all we want to consider the product form of it, right? If at all we want to consider the product form of it, when we take product, it is e power minus z into e power minus z. Anyway, since that is not required, I'll just eliminate it. Now, we can keep the answer as e power minus z into 1 minus z itself. This is the expression for f dash of z. But what we need is f of z. Our question is to find f of z as a function of z. So to find f of z, we have to integrate with respect to z. So now integrating with respect to z, integrating with respect to z. So f of z is equal to integration of, the expression was 1 minus z into e power minus z dz plus c, the constant of integration. Now we have to integrate 1 minus z into e power minus z. So let us integrate it using the Bernoulli's rule of integration by parts. So f of z will be equal to, which is u term for us, u and v, uv rule we are applying, but we can apply Bernoulli's rule directly to write down integration by parts. So I am assuming this as u and e power minus z as v according to Eilate. According to Eilate, exponential comes last and the algebraic comes before it. So that is why 1 minus z should be assumed as u, e power minus z should be assumed as v. So let us integrate by applying Bernoulli's rule now. First function into integral of the second. So first I have to write down 1 minus z as it is. First 1 minus z as it is. Integration of e power minus z is e power minus z divided by minus 1. Minus according to Bernoulli's rule, differentiation of 1 minus z is minus 1 into integration of e power minus z is e power minus z divided by minus 1 the whole square. We are applying Bernoulli's rule of integration by parts. We'll just recall what is it, Bernoulli's rule of integration by parts. So it is nothing but first function u as it is, so 1 minus z as it is, integration of e power minus z is e power minus z divided by minus 1. According to Bernoulli's rule, it is minus in the middle. Then differentiation of 1 minus z is minus 1 into, once again when we integrate e power minus z by minus 1, we get e power minus z by minus 1 the whole square. Plus the constant of integration we will retain as it is, plus c. Now we will simplify this. We have minus sign here, so it is minus of e power minus z. So let us rewrite f of z expression first. So f of z is equal to, we have minus of 1 minus z multiplied by e power minus z, and there is minus into minus plus e power minus z plus the constant of integration c. Minus 1 the whole square is 1, minus of minus is plus 1 into e power minus z. So that is why we have plus here. Now let us multiply this inside the bracket and rewrite f of z. So f of z is equal to minus e power minus z, minus of minus plus z into e power minus z plus e power minus z plus the constant of integration c. We observe that one of the term get cancelled here, that is minus e power minus z gets cancelled with plus e power minus z. So once it cancels, what do we remain is f of z is equal to, a simple function is remained, which is z into e power minus z plus the constant of integration c. So the first part of the problem was to find f of z as a function of z, and we have obtained f of z as z into e power minus z plus the constant of integration c. Now the second part of the problem is hence find v. So we have to find out the imaginary part now. Now in order to find the imaginary part, we use f of z function whatever we have obtained just now, that is z into e power minus z, and substitute the Cartesian representation for z in the right hand side, and in the left hand side we substitute f of z as u plus iv. So we'll write down the same thing now. To find v, now we consider first f of z, whatever we obtained. Consider f of z is equal to z into e power minus z. We ignore the constant of integration, or we can assume c equal to 0. Constant of integration c is assumed to be 0. So this is the f of z function what we obtained. Now left hand side f of z is nothing but u plus iv. Let us substitute u plus iv in the left hand side, and in the right hand side z is nothing but x plus iy multiplied by e power minus of x plus iy. Correct? Z in the Cartesian representation is x plus iy. So in the power also we are substituting x plus iy. Purpose of doing this is we have to expand this e power minus of x plus iy, and we need to obtain the real and imaginary separately. Equating the real and imaginary separately, we will be able to obtain both u and v. U will be the given function u, and respective v also we can obtain. So a kind of verification it becomes actually, right? So let us see how is it. So we'll just continue. This is x plus iy as it is. Then we can split this as e power minus x into e power minus iy. So that this x plus iy into e power minus x as it is, e power minus iy can be written as cos y minus I into sin y. Cos y minus I into sin y. Now we have to multiply. So first I will write down e power minus x term as it is. Let us multiply x plus iy with cos y minus I sin y. Right? Let us multiply that first. So we have x into cos y. X into cos y. First I will multiply x with both the terms. X into cos y minus I into x into sin y. Then the second term is plus iy cos y, and we have last term I into I square, which is minus 1, and plus into minus, we actually have plus into minus minus, I square is minus 1. So minus of minus becomes plus y into sin y. Y into sin y. So this gives us e power minus x multiplied by, we'll group all the real terms together. So we have x into cos y plus y sin y. These are the real terms. And in the imaginary term, I'll write down plus I e power minus x first outside. What are all the imaginary terms we have? We have y into cos y minus x into sin y. Minus x into sin y. Now we have to obtain the imaginary term, that is v. Now we can equate real and imaginary on both sides. No, remember the left hand side is nothing but u plus iv. U plus iv. So u is, when I equate the real term, I should get back the given u. Now given u is e power minus x into x cos y plus y sin y. Let us just check that once. Given u is e power minus x into x cos y plus y sin y. So we have already obtained the same thing, x cos y plus y sin y. So a kind of verification for us that whatever we have done is correct or not. Then now obtaining the imaginary or equating the imaginary, I can obtain v equal to e power minus x multiplied by y cos y minus x into sin y. So I'll just conclude here itself. Equating the imaginary part, we can obtain v. V is equal to e power minus x multiplied by y cos y minus x into sin y. Minus x into sin y. E power minus x multiplied by y cos y minus x into sin y. Correct? So this is how we obtain f of z given real or imaginary part. First we can obtain f of z followed by finding the other one. That is, in this question, real part was given and we had to obtain the imaginary v later on. It might be vice versa also. Second problem. If phi plus I psi represents the complex potential, represents the complex potential of an electrostatic field of an electrostatic field where psi is given for us. Psi is equal to x square minus y square plus x divided by x square plus y square. Find f of z and hence determine phi and hence determine phi. So very firstly, let us observe that the given question is in the form of phi plus I psi. Instead of u plus iv, they have mentioned the question in the form of phi plus I psi. So in place of u, we can have phi, and in place of v, we can have psi. So imaginary part psi is given for us. We have to find the analytic function f of z, and hence we have to determine the value of phi. Or instead, it is saying as imaginary is given, we have to find f of z and hence to determine the real part of it. So let us see the solution. The problem is going to be worked out in the same manner as we did the previous one. Instead of variables u and v, we have the variables phi and psi, that's all. So let's see the solution. Given psi is equal to x square minus y square plus x divided by x square plus y square. So first we will write down what is given for us, and we have to find out the partial derivatives psi x and psi y. Whichever the expression is given, with respect to that, we will find out the partial derivative with respect to x and with respect to y. So with respect to x, when I want to differentiate, differentiation of x square is 2x, differentiation of y square is 0, because partial differentiation we are doing. Now we have to apply the quotient rule for x divided by x square plus y square. So u by v rule. So it is v as it is into differentiation of u minus u as it is into differentiation of v, the whole divided by v square. Let me explain you how this is exactly. So first we are applying the differentiation partially with respect to x. X square differentiation is 2x, y square with respect to x is 0. Then quotient rule for x by x square plus y square. So we are applying quotient rule u by v. V into differentiation of u minus u into differentiation of v, the whole divided by v square is the formula. So v means x square plus y square as it is. Differentiation of x is 1. With respect to x partially is 1. Minus x as it is. Differentiation of x square plus y square partially with respect to x is 2x. 2x plus 0 actually, so 2x. Divided by v square. So denominator term whole square. Now let us simplify this and rewrite the expression. So this will give us psi x is equal to 2x plus, if I'm not wrong, we get plus of y square minus x square divided by x square plus y square the whole square. We have x square minus 2x square here, which simplifies to minus x square. I wrote the positive term first, which is y square. So remaining is y square minus x square divided by denominator whole square as it is. This is psi x for us. Now, in the same manner, keeping psi, we have to differentiate partially with respect to y and find out psi y. With respect to y, we have to differentiate to find out psi y. With respect to y, differentiation of x square minus y square will be minus 2y plus, quotient rule is actually not required. So x is a constant in the numerator, writing it down as it is. Denominator is of the form 1 by t. Differentiation of 1 by t is minus 1 by t square. T square, so x square plus y square the whole square into chain rule. So y square differentiation is 2y. So let me explain this once again. We have 2x differentiation of x square minus y square partially with respect to y is minus 2y. Then for the next term, we actually have x divided by x square plus y square. X is a constant when we differentiate partially with respect to y. So keeping x as it is, I can differentiate only 1 by x square plus y square, which is of the form 1 by t. 1 by t. So differentiation of 1 by t is minus 1 by t square. So x square plus y square whole square. Into, with respect to y, so chain rule, y square differentiation will be 2y. With respect to y we are doing. Let us simplify this and rewrite the expression. So psi y is equal to minus 2y minus 2 into x into y divided by x square plus y square the whole square. We can actually apply quotient rule also. If you apply quotient rule also, you'll get the same answer. I just did it in the easy way by taking numerator x constant, keeping it as it is. Right? So this is psi y for us. Now, keeping the psi x and psi y, we need to consider the expression for f dash of z. So consider the formula for f dash of z. So f dash of z is given by ux plus I dx. Here it will be phi x plus I into phi x plus I into psi x. It is of the form phi plus I psi. Given function was of the form phi plus I psi instead of u plus iv. So we had to write it down in the form ux plus I dx. Here it will be phi x plus I into psi x. Now we know psi x to substitute, but we don't know phi x. So let us use CR equations for phi x. So using CR equations, let us rewrite phi x is equal to psi y. So how did we write down like that is, we recall CR equations with respect to u and v first. Ux is equal to vy and vx is equal to minus uy. Now I want to change ux term, real term. So ux is equal to vy. That is how we are getting phi x is equal to psi y. We'll substitute this here. So we'll rewrite f dash of z now. So therefore f dash of z is equal to f dash of z is psi y plus I into psi x. Now we know psi y, we know psi x, both we have just now obtained the partial derivatives. We need to substitute both of them to obtain f dash of z. So substituting, we get f dash of z here. So f dash of z is equal to, it is psi y plus I into psi x. So first I will substitute psi y, which is minus 2y minus 2 into x into y divided by x square plus y square the whole square. This is psi y for us, plus I into psi x. So I into psi x is nothing but 2x plus y square minus x square divided by x square plus y square the whole square. X square plus y square the whole square. Let us just check the substitution ones. The first one should have been psi y and the second one is psi x. Yes, this is psi x. Now immediately we will make use of the Milne-Thomson substitution. Using Milne-Thomson substitution, we put x is equal to z and y is equal to 0. Substitute x is equal to z and y is equal to 0 in the previous expression. So we have f dash of z is equal to, f dash of z is, since y is 0, first term and second term both are 0. So entire real term is 0 plus I into, the imaginary term will be 2 into z plus 0 minus z square divided by z square the whole square. Let's check it out. We have everywhere y equal to 0. So since y is 0, this is 0 and second term also becomes 0. So entire real term becomes 0. Plus I into, imaginary term is 2z. X is equal to z, we are substituting. So 2z. Then y is 0. So 0 minus z square is minus z square divided by z square the whole square. Because x square whole square. Y is 0. right? Let us simplify and rewrite this expression for f dash of z. So f dash of z we obtain as I into 2z minus z square divided by z power 4. So simplifying this, f dash of z is an imaginary function, let it be. So we have 2z minus 1 by z square. Minus 1 by z square. This is f dash of z. Our aim is to obtain f of z as a function of z. So to obtain f of z as a function of z, we integrate with respect to z. Integrate with respect to z. So we have f of z. F dash of z integration is f of z. Integration is I is a constant, so integration of 2z minus z square. 2z minus 1 by z square into dz plus the constant of integration c. 2z minus 1 by z square is the expression what we obtain now. So 2z minus 1 by z square. Integration. So we obtain integration now. So this becomes f of z is equal to I into integration of 2 into z is 2 into z square divided by 2 minus integration of 1 by z square is minus 1 by z. So minus of minus becomes plus 1 by z. How did we obtain integration of 1 by z square? Z power minus 2 in the numerator. So integration of z power n is z power n plus 1 divided by n plus 1. So z power minus 2 integration, you will get it as, I'll just show it here in the rough work. So this is because of the reason that we have integration of z power minus 2. So z power minus 2 integration we need to obtain, no? dz. So this is z power minus 2 plus 1 divided by minus 2 plus 1. So this gives me z power minus 1 divided by minus 1, which is minus 1 by z. But we observe there is a minus sign here in the integration part. So minus of minus becomes plus. So that is how we are able to obtain the integration for this. Now what is the answer finally then? Therefore f of z is equal to, f of z is I into 2 get cancelled. So we have z square plus 1 by z plus the constant of integration c. So this is the first part of the problem. The function is imaginary, let it be. You can also have sometimes real plus imaginary function as a function of f of z. Sometimes it will be only the real part, sometimes it will be only the imaginary part. This is how we obtain f of z. Now next part of the problem is to find the imaginary. Real was given, the imaginary part psi was given for us. We had to find out now phi. To find phi of x comma y. To find phi. Phi is a function of x comma y. To find phi, we consider f of z, whatever we obtained just now, and substitute the Cartesian representation for z. So consider f of z is equal to whatever we obtained just now. Consider f of z given as I into, just now we obtained this, no, z square plus 1 by z. We ignore the constant of integration or assume c equal to 0. C equal to 0. So this is f of z function for us. Keeping f of z function, now we will substitute f of z as u plus iv and right hand side z as x plus iy and simplify further. So this will become u plus iv is equal to I into z square, which is x plus iy the whole square plus 1 divided by x plus iy. 1 divided by x plus iy. Throughout the Cartesian representation, we are writing it down. So this is equal to, let us obtain, simplifying this, we need to equate the real and imaginary, no? That is why. So this becomes x square minus y square plus I into 2 into xy plus, this is for x plus iy whole square terms. I'll just put a bracket. 1 divided by x plus iy we need to rationalize. So this becomes x minus iy divided by x plus iy into x minus iy. Denominator will be x plus iy into x minus iy. So let us simplify this. I'll just explain how is this. X plus iy the whole square we have now. It is a plus b whole square formula. A square plus b square. But iy whole square becomes minus y square. Plus 2ab term. So 2 into I into xy. So 2 into xyi. Plus rationalize the second one. Multiply by its conjugate. So x minus iy divided by x plus iy into x minus iy. Okay. Now we need to simplify this by expanding this denominator. First we will keep the first term as it is for time being. So we have I into, this is x square minus y square plus I into 2xy plus x minus iy divided by denominator, it will be x square plus y square. Let us check how it is. We have a plus b into a minus b formula, a square minus b square, but b square will be iy whole square. I is minus 1, so minus of minus becomes plus. That is how we are getting plus sign here. Now we can group all the real terms together and imaginary terms together. That is one way of doing. The other way of doing is, first we will multiply this I inside the bracket. Whenever we multiply the I inside the bracket, it will be easy for us to do or go ahead with it. So let us multiply I inside and write down. So this becomes u plus iv, or instead I have to take actually 5 plus I side. Yeah, left hand side I should have written 5 plus I side. Right here I should have written 5 plus I side, because we are doing with phi and psi terms, no? I'm sorry. So this will be now equal to 5 plus I side is now equal to, we'll multiply I inside as I mentioned. So we have I into x square minus y square minus 2xy minus 2 into x into y plus I into, I'll explain, I into x divided by x square plus y square. Then the last term will be plus y into x square plus y square. So while I am multiplying this I inside, I am taking care that I is multiplied with the real term x square minus y square. Then the second term I into I becomes I square, which is minus 1. So minus 2xy it will be, minus 2xy. Again, I into real term x by x square plus y square. So I into x by x square plus y square. And lastly, I into minus I. I into minus I is minus I square, which is plus 1. So plus y divided by x square plus y square. So that now I can group the real and imaginary terms easily, no? So this becomes 5 plus I psi is equal to real terms. Which are all the real terms? I'll write down it here. So it is minus 2x into y plus y divided by x square plus y square. These are the real terms for us. And let me group all the imaginary terms separately. So this will be x square minus y square plus x divided by x square plus y square. And this was our given psi, no? The given psi was x square minus y square, x square minus y square plus x divided by x square plus y square. Right, this was our given psi. So we have arrived it correctly. Now this will be equated to 5. Our aim was to obtain the value of 5. So let us conclude. Thus phi is equal to equating the real part. So thus phi is equal to minus 2xy plus y divided by x square plus y square. So this is how we can obtain the real part of the expression given the imaginary for us, finding f of z, the analytic function f of z first. So these were the problems which I wanted to consider on Cartesian representation. Now next we will move ahead with polar representation. Third problem. Determine or find, we can write down, find the analytic function, find the analytic function if v is equal to minus sine theta divided by r, and hence find u. Hence find the real part u. So in most of the problems I am trying to consider both the f of z part as well as the finding real or the imaginary part, so that it is convenient for us to understand how to do. So let us see the solution for this. So solution, given v is equal to minus sine theta divided by r, let us find out the partial derivatives vr and v theta. With respect to r, when I want to differentiate, minus sine theta is a constant. Differentiation of 1 by r is minus 1 by r square. So minus of minus becomes plus. Similarly, with respect to theta, differentiation of sine theta is cos theta, keeping minus sign and the r as it is. So Vr and V theta partial differentiations with respect to r and theta we have found out. Now we consider the expression for f dash of z. Consider f dash of z in a polar representation. It is given by e power minus I theta into ur plus I into Vr. We have already seen this in the derivation of CR equations. While we derived CR equations itself, we have seen this. So this is the expression for f dash of z. We observe that we are familiar to substitute Vr. Vr we can substitute sine theta by r square. Whereas V theta we are not aware. So since we are not aware of V theta, we use CR equations and change the term for UR. So using CR equations, we have R into UR. R into UR is equal to V theta. So from this I can write down UR is equal to V theta divided by R. So we can write down UR is equal to V theta divided by R from this now. So we will substitute UR place as V theta divided by R and then substitute both the partial derivatives. So let us do that. So we can rewrite f dash of z expression now. So therefore f dash of z is equal to e power minus I theta into 1 by r v theta plus I into Vr. Now since we know both these partial derivatives, we can substitute both of these partial derivatives and rewrite f dash of z. So this will become e power minus I theta into v theta. V theta is minus cos theta divided by r. So this becomes minus cos theta divided by r square plus I into Vr. Vr is nothing but sine theta divided by r square. So V theta is nothing but minus cos theta by r. Already we have an r in the denominator, so it becomes r square in the denominator. Vr we are substituting directly sine theta divided by r square. So those are the values now. Let us just check once and come back. And we now substitute Milne-Thomson substitution. So we make use of the Milne-Thomson substitution in the polar form. So using MTS, Milne-Thomson substitution, we put r is equal to z and theta is equal to 0. Substitute r is equal to z and theta is equal to 0 so that we can obtain f dash of z as a function of z. So f dash of z will be now equal to e power 0 multiplied by minus cos 0 divided by z square plus I into sine 0 divided by z square. So we recall the standard values. Sine 0 is 0, cos 0 is 1. So with that we can obtain f dash of z as a function of z, which is minus 1 by z square. Minus 1 by z square. Now we need to integrate with respect to z to obtain f of z as a function of z. Integrating with respect to z, we can obtain f of z as a function of z. So this will be f of z is equal to integration of minus 1 by z square dz plus the constant of integration c. So integration of 1 by z square we already saw in the last problem. This is 1 by z plus c. So how is it 1 by z? Using the formula for z power n is equal to integration of z power n is z power n plus 1 divided by n plus 1. So integration of z power minus 2 will be z power minus 2 plus 1 divided by minus 2 plus 1. And there's already a minus sign, that is why minus of minus becomes plus. So 1 by z plus c is the answer. This is the first part of the problem. Now to find second part of the problem, that is to find u. Given imaginary part, after finding f of z, we were supposed to find u. So let us find u now by considering f of z. So f of z is equal to 1 divided by z. We ignore the constant or take the constant of integration c is equal to 0. Now we use polar representation of z in the right hand side because we are dealing with a problem based on the polar form. So r e power I theta. And this can be written as 1 by r into e power minus I theta taking to the numerator. E power I theta we took it to the numerator. Why? Because now we can use e power minus I theta as cos theta minus I sin theta. So we have u plus iv is equal to u plus iv left hand side is equal to the right hand side is 1 by r into e power minus I theta is cos theta minus I into sin theta. Multiplying 1 by r, so we have 1 by r cos theta minus I into 1 by r sin theta. Now equating the real part, what we want is u. So let us equate the real part to obtain u. Hence u is equal to 1 by r cos theta. And we observe that the given v was nothing but minus 1 by r sin theta itself. Let us check that once. This becomes actually a verification. So v is minus 1 by r sin theta. Minus 1 by r sin theta. So we obtained the correct v. So we can aramse obtain u equating the real part, which is 1 by r cos theta. So this is how we work a problem in the polar representation. Now we'll see one last problem again in the polar form to understand better well. So determine the analytic function or find the analytic function f of z. Find the analytic function f of z whose imaginary part is it is given as r minus k square divided by r multiplied by sin theta, and it is given that r is not equal to 0. If r becomes 0, this becomes an infinite value. Hence find the real part. So real part is nothing but u. Given imaginary part for us, that is v is given for us. So let's do the solution. Given imaginary part, that is v is r minus k square divided by r multiplied by sin theta. Let us find out the partial derivatives with respect to r and theta. So with respect to r, sin theta is a constant. Differentiation of r is 1 minus k square as it is. Differentiation of 1 by r is minus 1 by r square. So this becomes plus here, minus of minus, keeping sin theta as it is. Similarly, when I want to differentiate with respect to theta, v theta will be keeping r term as it is. So r minus k square by r as it is. Differentiation of sin theta is cos theta. cos theta. I'll repeat the differentiation. With respect to r, differentiation of r is 1. K square is a constant. Differentiation of 1 by r is minus 1 by r square. There is a minus outside, so minus of minus becomes plus. Keeping sine theta constant as it is. We are dealing with partial differentiation concept. Now v theta means dou v by dou theta. Partial differentiation with respect to theta. Keeping the r term as it is, differentiation of sine theta is cos theta. Now the purpose of finding these partial derivatives is to consider f dash of z expression. So let us consider the expression for f dash of z. It is given by e power minus I theta into ur plus I into vr. Now again we are familiar with vr to substitute. Vr we are aware to substitute, but we don't know ur. So we need to use CR equations and change ur. So using CR equations, r ur is equal to v theta. So this gives us ur is equal to v theta divided by r. V theta divided by r. So we will substitute ur as v theta divided by r and simplify further. So this gives us f dash of z is equal to, we have e power minus I theta into 1 by r v theta plus I into vr. Now we know both vr and v theta to substitute. So let us substitute both the derivatives what we already obtained. So e power minus I theta into 1 by r v theta. So it will be 1 by r into r minus k square divided by r multiplied by cos theta plus I into vr. Vr term let us substitute, which is 1 plus k square divided by r square multiplied by sine theta. Let us just check whether we substituted correctly. V theta and vr term we are trying to substitute. So v theta is r minus k square by r cos theta, r minus k square by r cos theta, and I as it is vr. Vr is nothing but 1 plus k square by r square sine theta. 1 plus k square by r square sine theta. Yes, we have substituted correctly. Now let us make use of the Milne-Thomson substitution. So we always use this to make our work easy. We substitute r is equal to z and theta is equal to 0 in the polar substitution. It is Milne-Thomson substitution in the polar form. So this helps us to obtain f dash of z as a function of z. So that will be e power 0 outside. Then we have 1 by z into z minus k square divided by z multiplied by cos 0 plus I into 1 plus k square divided by z square multiplied by sine 0. Recall the standard value, sine 0 is 0. So since sine 0 is 0, the entire imaginary term vanishes. Since sine 0 is 0. Now we just have this cos 0 equal to 1. So let us substitute f dash of z as f dash of z is equal to, we have 1 divided by z multiplied by z minus k square by z. Cos 0 is 1, e power 0 is also 1. Now multiply 1 by z inside, you will get f dash of z is equal to 1 minus k square divided by z square. F dash of z is 1 minus k square by z square. So this is f dash of z for us. But our aim is to find f of z as a function of z. So to find f of z as a function of z, we have to integrate on both sides with respect to z. So integrating with respect to z, we can obtain f of z, which is integration of 1 minus k square by z square dz plus the constant of integration c. So So this gives us f of z is equal to integration of 1 is z. Integration of 1 by z square is 1 by z minus 1 by z square. Integration of minus 1 by z square is 1 by z. So this gives us the answer plus k square by z. What is the constant of integration? C. So f of z is z plus k square by z. So this is the required answer for f of z, which is the first part of the problem. Now the second part of the problem is to find u, the real part. To find u, let us consider the expression for f of z, whatever we obtained just now. We obtained as z plus k square divided by z. We ignore the constant or take constant of integration c is equal to 0. With this we substitute polar representation on right hand side. Substituting f of z as u plus iv, we substitute polar representation. The question is a polar form, that is why. Plus k square divided by z. Z is r e power I theta. R e power I theta. So this helps us now to split. Before I split, I have to first write down that e power I theta in the denominator to the numerator will write on. So this is f of z is nothing but u plus iv, no? So left hand side is u plus iv is equal to right hand side. First I will keep this r e power I theta as it is. Next term k square divided by r as it is first. E power a minus I theta, let me write down. So that now I can substitute e power I theta as cos theta plus I sin theta, and here e power minus I theta as cos theta minus I sin theta. Okay, both LHS and RHS will substitute. So u plus iv is equal to r into cos theta plus I sin theta. Right hand side k square divided by r as it is. E power minus I theta is cos theta minus I sin theta. Now we can multiply r inside for the first term here, and for the second term we can multiply k square by r inside the bracket, so that later we can separate the real and imaginary parts. So u plus iv is equal to r cos theta plus I into r sin theta plus k square divided by r cos theta minus I into k square divided by r sin theta. The purpose of multiplying the outside constant inside is we need to now group the real and the imaginary terms. Let us do grouping and then equate the real and imaginary on both sides. Grouping. So let us group all the real terms. R cos theta plus k square by r cos theta. These are the real terms, no? Plus I into, which are the imaginary terms here? R sin theta minus k square by r sin theta. These are the imaginary terms. Minus k square by r. I common I took. So here r sin theta remained, here minus k square by r sin theta remained. So these are the imaginary terms. Now let us verify. Given v was, taking sin theta common, it was r minus k square by r. Taking sin theta common, given v was r minus k square by r. Let us just check that once. R minus k square by r into sin theta. This was our given imaginary part. Imaginary part. Now in the real part, when I equate, I have to equate and obtain the real part of it. Taking cos theta common, I can directly write down r plus k square by r. So hence the real part u is equal to r plus k square divided by r multiplied by cos theta. Again the restriction follows. R is not equal to 0. If r becomes 0, this becomes an infinite value. That is the reason we write down this restriction for r, that it is not a 0 value. So this is how we do problems based on the type 2 category. Type 2 category was to find the analytic function f of z given the real or imaginary part. Hope you have followed these problems. Thank you for watching.